Justin Miller, Rockstar College Physics here. We've got ourselves another incline plane problem that we'd like to investigate. So let's just go ahead and do that, shall we? Yeah, that sounds good. All right, so yeah, here's the problem. All right, so as was stated, we're going to take ourselves a 2.5 kilogram mass and we're going to put it on an inclined plane of 35 degrees, and then we're going to attach a rope to it and we're going to pull upward on that mass and produce an acceleration of 1.50 meters per second squared. We're going to say, well, what does the tension in the rope have to be? So try to kind of do this. Get myself a little string here and a mass, you'll see here in a second. Alright, stick that there, and get myself a rope or string. Just a finger, whoa, get me. Alright, living dangerous, alright, I love it. Stick that there. Okay, I was able to do this. Fantastic. So we're going to take this rope here, and it doesn't matter that I'm pulling on it, it's the rope that's pulling on the mass. That's what we're concerned with. And we want to produce an acceleration up the incline of 1.5 meters per second. So I'm not going to do it exactly 1.5 meters per second, but it's initially at rest and it goes faster and faster. We're going to pull it straight up the incline. I don't want an angle in the rope, so this rope should stay parallel to the incline. Like that, faster and faster. Notice if I don't pull on it, it slides down the incline. Great, we already know that that should happen. But this is basically what we've got going on. What is the tension in the rope that's necessary to produce that acceleration? That's part A, and then we'll mess around with that tension a little bit and see what else could possibly occur. All right, so here we go. We'll just go ahead and take our system here. We've got theta for the incline is 35 degrees. We've got the mass that we're attaching is 2.50 kilograms. We'll go ahead and stick the mass on here. And we'll just go ahead and attach a rope to it too, right? Rope of negligible mass. We're ignoring the mass in the rope, or just saying it's a string, light string. All right. So we want this mass to, again, have an acceleration of 1.50 meters per second squared. And that's pretty much that. So what do we need here? Let us draw on the forces, shall we? That would be a good idea. So we've got some forces acting, right? We've got the gravitational force perpendicular to the incline, Fg perpendicular hat. We've got the normal force. We've got the parallel component of the gravitational force, Fg parallel hat. And we also got the force of tension, right, transmitted by this rope. So this, we've got ourselves some T hat, force of tension. And this is what we've got going on. So what do we do with all of this? We start to analyze it. We know that the acceleration is constrained to be parallel to the incline, and that should provoke us to investigate the forces that are parallel to the incline then. Note that there are no other forces other than the normal force and the perpendicular component of the gravitational force that are acting perpendicular to the incline. So what's going to happen with those? They cancel each other out. They're not contributing to the motion of the object or changes in motion of the object whatsoever. We don't need to even look at the perpendicular components. All the motion's constrained in the parallel direction. So we start off. Hey, we want to know what is T hat, right? So net force parallel to the incline produces the acceleration of the mass parallel to the incline. Net force produces, and then we've got net force is composed of. Well, the net force parallel to the incline is composed of the force of tension and the parallel component of the gravitational force. Thus, from these two, we've got ourselves that T hat plus Fg parallel hat must be equal then to MA parallel hat, where A parallel is the overall acceleration. So what do we do with this? Well, we're trying to solve this out for t hat, right? We'll just get everything except t hat, isolate t hat, we'll just say. So we can move that FG parallel hat to the other side and write ourselves that t hat is equal to MA parallel hat minus FG parallel hat. All right, we got a nice vector representation of what t hat must be equal to, and now it's the time to solve out for it, right? So this object we're going to say is accelerating up the incline. We got to pick a directionality associated with up versus down, or a sign associated with those. So we're going to say for directions, let up equal plus and down equal minus. You're free to pick it the other way, doesn't really matter, but this would be the inherent direction of motion if it started at rest, so I pick it to be the positive direction. What does that do for us? Well, that makes our A parallel hat positive because A parallels up the incline, and it makes FG parallel hat a negative quantity because it is down the incline. So when we write these out, we have that A hat is equal to positive 1.5 meters per second squared. The plus sign means up. And we've got FG parallel hat is equal to negative FG parallel. This is the magnitude. This is the direction. So we could go a step further because we know that FG parallel is equal to, well, we've got the negative sign for the hat, and then minus mg times the sine of theta sub I. So that's what FG parallel hat looks like in terms of the sign composition that we've embedded in the system. Minus is down. So let's put this stuff in here, right? We've got t hat is equal to, well, m is 2.5 kilograms. We've got A is 1.5 meters per second squared, keeping it positive because it's up. And then we've got minus, then FG parallel hat. FG parallel hat is this right here. So what do we put in? Well, we put in minus mg times the sine of theta sub I. Minus minus becomes plus, and then we can go ahead and put in what is m, what is theta. We know what g is. We can write this out as t is equal to 2.5 kilograms multiplied by 1.5 meters per second squared plus 2.5 kilograms times g times the sine of 35 degrees. And what does that give us overall? That is C, right? We got 2.5 times 1.5 plus 2.5 times 9.8 times the sine of 35. We got ourselves 17.803. 17.803 newtons. This came out to be positive, right? Right. What does positive mean? Positive means up the incline. So in the end, we've got ourselves that t hat is equal to 17.8, three significant figures. I'm just going to write them all out here. 17.803 newtons up the incline. So we've got the magnitude here and the direction clearly stated. So what I want to do at this point is actually switch my sign convention just to show it's arbitrary. You can pick whatever you want. You just have to stick with it. So we're going to go back. Going back. And now using up is equal to minus and down is equal to plus. So we're going to switch things around. So we're going to go ahead and start with what we already know, vector representation. T hat is equal to MA hat minus FG parallel hat. That's independent of any signs. That's what we got to right here from just analyzing the forces acting. And now we want to go ahead and say, well, what about our sign conventions, right? Well, using this, we now have that A hat is going to be, well, up's the negative direction now. We're changing it. So A hat is going to be negative 1.5 meters per second squared. The negative says up. Now positive's down, so we've got ourselves the FG parallel hat is just equal to positive FG parallel, which is just going to be our mg times the sine theta sub I. So let's see what happens when we go ahead and stick that stuff in here and get rid of these hats here and replace them with the sign convention that we're choosing to represent them. So now we've got, say now, with our signs for directions. It's supposed to be a C. For directions, we've got the T hat is equal to M times negative 1.5 meters per second squared minus, well, mg times the sine of theta. Let's put in all our quantities here. We've got the T hat is equal then to 2.5 kilograms multiplied by negative 1.5 meters per second squared minus 2.5 kilograms times g times the sine of 35 degrees. Well, these are all the same quantities that we had here, right? Except now this term's negative and this term's negative. Negative, negative. What are we going to get? Stick it in your calculator and you're going to get yourself negative 17.803. Oh, now we got a negative answer. Oh shoot, does that mean something went wrong? No, it doesn't, because we said that negative is up the incline directionally. So when we went ahead, or when we go ahead and say, what is T hat? T hat is 17.803 newtons, and negative means up the incline. It says up the incline. So we get rid of it here and we state it out. Up the incline. So overall, what do we get? We get the same exact answer. We just flip the sign conventions that we use. It doesn't matter. It still works out because we keep track of it and we take it into account. All right. So let's answer the last two parts of this question. Just wanted to make sure we're on the same page with those sign, not conventions, I should say, but sign correlations with the direction. And now, what are we going to do? Well, we're going to have the force of tension change. Now we're going to say, well, what happens if the force of tension is actually 30 newtons up the incline? So part B, let T hat be equal to 30 newtons up the incline. What acceleration is produced? So if we're still dealing with just parallel stuff, right? Now we've got like A hat is equal to what? Well, before we're pulling with a force of 17.803 newtons up the incline. Now we're going to pull 30 newtons of force. What do you think we're going to end up getting? A bigger acceleration, that's right. Because the force of tension up the incline is greater than it was previously. So if that's the expectation, this object will accelerate up the incline still, but at a greater rate than just 1.5. So let us check this out, right? So we just go back. T hat plus FG parallel hat gives us MA hat. Net force produces, net force is composed of in the parallel direction, just like what we had before. And we're solving this out for A hat. Well, let's just choose a sign convention, right? So let's just still say that up is equal to the plus direction and down is equal to the minus direction. T hat is equal to then plus 30 newtons and FG parallel hat is equal to negative mg times the sine of theta sub I. It's down, tension's up. Up, down. So what do we do with this? Well, we'll go ahead and put in these sign conventions, and we can go ahead and say, well, we can divide this out by m. Let's do this first. A hat is equal to t hat plus f sub g parallel hat divided by m. And then in our sign conventions, a parallel hat is equal to 30 newtons plus negative mg sine theta, so minus mg times the sine of theta sub I divided by the mass n, which gives us the A parallel hat is then equal to 30 newtons minus 2.5 kilograms times g times the sine of 35 degrees divided by 2.5 kilograms. So, I just solved this out, right? We've got ourselves 30 minus 2.5 times 9.8 times the sine of 35. That divided by 2.5. We get ourselves 6.378. .378 meters per second squared. There is the overall acceleration up the incline now. Much greater than just the 1.5, right? Well, we haven't even doubled this force here, but we've come out and gotten a much, much larger acceleration. Why may that be? Well, we gotta go back to see what the net force is and compare it to the net force in the previous case. That's what it's all about, right? So previously, part A, what was the net force parallel to the incline? Well, that was T hat plus F sub G hat. Well, that would have been our 17.803 minus mg sine theta. 17.803 minus mg times the sine of theta. Whereas for part B, the net force parallel is going to be equal to, well, 30 minus mg sine theta. 30 newtons minus mg times the sine of theta. It's the net force that produces the overall acceleration, so that's what we really want to compare. Not just force of tension and say, wait, we got way over double. How did that happen? Well, it's all about the net force. So compute this out, right? We got 17.803 minus 2.5 times 9.8 times the sine of 35. And for this, we got that the net force for part A was equal to 3.75 newtons. Now for part B, it's going to be much, much greater than that. Let's see. We've got 30, and we could get it a different way. Let's just do it like this. 30 minus 2.5 times 9.8 times the sine of 35. We get that the net force here is equal to 15.947. Look at this. This is almost in between like 4 and 5 times greater than this. So the acceleration between part A and part B should be somewhere between 4 and 5 times greater for part B relative to part A. Well, if we went ahead and did 6.378 and divided that by 1.5, we get about 4.252. That means the acceleration for part B was 4.252 times greater than that for part A. Well, that's this same ratio, right? If we take 15.947 and divide it by 3.75, 4.252. The ratios are the same because, well, they're both proportional to the mass. Or, excuse me, the mass is the constant of proportionality. They are proportional to each other. Net force is proportional to the acceleration. So that's where the discrepancy is. Not discrepancy, but where it may trick you a little bit and say, wait, we've only not even doubled the force of tension, but we come up with a much greater acceleration. There's a reason for that. There it is. All about the net force. All right, one last part here, and that'll be that for this problem. What happens if we go ahead and say, you know what? I'm going to have that tension reduced down to 10 newtons now. What is the acceleration of the mass? So we're still with this right here, this system. We're going to change the force of tension, and what do we get? See, now we're going to let the force of tension be equal to 10 newtons up the incline still, and say A hat is equal to what? Well, we've still got ourselves that T hat plus FG parallel hat is equal to MA parallel hat. Let us still stick with up is equal to plus, down is equal to minus for our directions, which gives us that T hat is equal to 10 newtons, positive, and FG parallel hat will be equal to negative mg times the sine of theta sub I, negative because it's down. Can go ahead and say again that A parallel hat is equal to T hat plus FG parallel hat divided by m, and then we can go ahead and throw in our sign correlations for these vector quantities, get rid of the vector hat in favor of their sign, and get ourselves A parallel hat is equal to 10 newtons minus mg times the sine of theta divided by m, which then gives us that A parallel hat is equal to 10 newtons minus 2.5 kilograms times a g times the sine of 35 degrees divided by 2.5 kilograms. So let's compute that out and see what we get. We got 10 minus 2.5 times 1.8 times sine of 35, and then that divided by 2.5. Oh my gosh, I get a negative answer. Whew. What does that even mean? We get negative 1.621. Negative 1.621 meters per second squared. What does negative mean? Negative means down the incline. Down the incline. Well, what we've got then is that A parallel hat for this part C is going to be equal to 1.621, 1.621 meters per second squared down the incline. That would be how we state our final answer. Reinterpret the sign as the direction. So how can we be pulling upward on it, but it's still going down? We're not pulling upward on it with enough force for it to actually go up the incline. That's definitely possible, right? You can see that there's tension in the string. What happens if, well, look at, there's still tension in the string that's going down the incline though, right? If I don't pull upward on it hard enough, it wants to accelerate down. If I let go of it, it does what it's going to do due to gravity. But I can still have that there's tension in it that reduces what it would be in the absence of that tension, but that it still accelerates down the incline. I'm doing a little bit too much, but still tension, still going down. So that's what we've got. We just don't have enough tension in the rope to actually pull it up, or for that matter, to keep the net force equal to 0, to keep the object at rest, because there is a certain amount of force that we can apply via tension that exactly balances out the gravitational force down the incline. And what happens then? Net force is equal to 0, no change in motion. The object's at rest, it remains at rest. I have a little bit more tension, starts going up. I have a little bit less tension than that, starts going down. And that's what we've got going on. So pretty nice problem. Again, sign conventions are really important, and I should say sign correlations, because it's up to you to pick. You have to pick it, then stick with it. All right, that'll be that. Yeah, more to come for sure. Have a good one. Until next.